In this module, we're going to be considering moving reference frames. It is important to keep in mind that position, velocity, and acceleration are not properties of an object, but are instead descriptive quantities measured relative to some reference frame. A reference frame, well, it's one or more coordinate systems that are fixed in space relative to each other. For example, you might be sitting in a laboratory, and you might want to measure the position and velocities of objects moving around in space, and you're going to do that relative to your laboratory. So you would have a coordinate system fixed in your laboratory and measure everything relative to that. You might even have a second coordinate system fixed in your laboratory with maybe the axes rotated a little bit. But as long as they're fixed in space with respect to each other, they're associated with the same reference frame. Now we can use multiple reference frames to describe the kinematical quantities associated with some object moving through space. We often associate a reference frame with some observer or with a moving object. So in addition to the reference frame of you sitting in a laboratory, maybe there is a train passing by outside your window, and somebody is sitting on the train, and they have a reference frame which is fixed relative to the moving train. To them, it's fixed, and they see the laboratory moving past them, and so it's very natural for them to have a reference frame fixed with them, but they can also see perhaps the objects in your laboratory moving around, and they can measure the positions of those objects relative to their coordinate systems in their reference frame. Two different reference frames that are at rest with respect to each other will, in general, describe objects with different coordinates, but the velocities and the accelerations of objects will agree. On the other hand, if the reference frames are moving with a constant velocity with respect to each other, then the velocities measured in the two frames will actually differ by this relative velocity, but the accelerations will still agree. And if the reference frames are accelerating with respect to each other, then the accelerations measured in the two frames will differ by this relative acceleration. More mathematically, this is all handled through what is called Galilean relativity. This simply says that the coordinates transform and velocities and accelerations add as simple vectors. Now I'm saying this is Galilean relativity because in reality this is not exactly how things behave. If you travel near the speed of light, then velocities and accelerations behave in a very different way. Now we're not going to go into all of this, and as long as you're not traveling anywhere close to the speed of light, Galilean relativity is a very, very good approximation. So this is what we're going to consider. So if we have a frame 1 and an object sitting there, we can see the position vector r sub 1 of that object measured relative to frame 1. And if we have another frame, frame 2, we can also measure the position vector of that object relative to frame 2. And the two frames, well, we can measure the relative positions of the origins of the two frames. And this position, this displacement vector, r sub 2, 1, will be related to the position of the object measured in frame 1 and the position of the object measured in frame 2 by the usual rules of vector addition, which simply gives us that r1 is equal to the relative displacement r sub 2, 1 of the frames plus r2, the position of the object as measured in frame 2. If we take a time derivative of both sides of the equation, then what we find is that the velocity of an object as measured in frame 1 is equal to the relative velocity of the two frames plus the velocity of the object as measured in frame 2. And if we take another time derivative, we find that the acceleration of an object as measured in frame 1 is equal to the relative acceleration of the frames plus the acceleration of the object as measured in frame 2. Now, just to recover the relationships we discussed just a moment ago, if the velocity, the relative velocity of the two frames, is not changing in time, then the acceleration as measured in the two frames will be the same for the object. And if the relative position of the origins of the two frames, so the displacement vector between the frames, is not changing with time, then the velocities of an object measured in the two frames is going to agree. Now, to see how all this works, let's consider an example. Assume we have a river that is flowing in some specified direction relative to the ground, and we have a boat that travels in the water. Now, we're going to have a reference frame that's associated with the ground, and somebody sitting in that reference frame will see the river flowing, and they'll see the boat moving through the river. Now, a boat traveling in a river, well, maybe it can see the ground nearby. Maybe the river is so large that it can't see the ground. It makes much more sense for the person in the boat to have a reference frame, which is the river. Okay, so we attach a new coordinate system to the river and have it flow with the river, and this will be our second reference frame, and we can measure the position of the boat relative to frame 2, just as we can measure the position of the boat relative to frame 1. And we can also measure the relative displacement of the origins of the two coordinate systems. And the velocity of the coordinate system, frame 2, relative to frame 1, in this case, is going to be the velocity of the river, because frame 2 is attached to the river and its motion. So we have three vectors here: the velocity, the relative velocity of the river with respect to the ground, the velocity v1 of the boat relative to the ground, and the velocity of the boat v2 relative to the river. All right, and based on the rules of Galilean relativity, what we know is that the velocity of the boat as measured in frame 1 is going to be the velocity of the river plus the velocity of the boat as measured in frame 2. Now, let's consider the question, what direction does the boat need to travel in the water to cross the river in the shortest distance? Well, the shortest distance is going to be, if the boat cuts straight across the river from one bank to the other without moving horizontally or in the direction of the flow of the river. That is, the shortest distance is going to be given when the boat travels directly across the river perpendicular to the flow of the river. Or, in more mathematical terms, our vector 1, velocity 1, for the velocity of the boat relative to the ground is going to be the speed of the boat relative to the ground in the j-hat direction. Now we know that the river is flowing with some speed, v river, in the i-hat direction. And so from our law of Galilean relativity, and just looking at the rules of simple vector addition, we see that the velocity of the boat as measured in frame 2 can be drawn by that red arrow in the figure. All right, well, we can also write this out mathematically. We see that in terms of components, the velocity of the boat relative to frame 2 is going to be minus the velocity of the river in the i-hat direction plus the velocity of the boat relative to the ground in the j-hat direction. So if we use the Pythagorean theorem, we know that the speed, or at least the square of the speed of the boat relative to the river, is going to be the square of the speed of the river plus the square of the speed of the boat relative to the ground. And we can use a little bit of trigonometry to find the angle of the boat relative to the horizontal direction. So tangent of theta is going to be just the ratio of the velocity, or the speed of the boat relative to the ground and the speed of the river flowing. Now, to answer our final question here, what direction does the boat need to travel, we need to calculate theta. But we don't quite have enough information yet to do this. To solve this problem, we need to either know the speed of the boat, v1, relative to the ground, or the speed of the boat relative to the water. More naturally would be to be given the speed of the boat relative to the water, and you would then be able to figure out the direction in the water you need to travel to go straight across the river. We would simply use, again, the Pythagorean theorem solving this time for V1 in terms of the velocity of the boat relative to the water, minus the, and square that, and subtract from that the square of the speed of the river, and take the square root, and that will give us the speed of the boat relative to the ground. Once we have that and we know the speed of the river, we can easily calculate the direction. Note that if the boat cannot travel as fast as the river is moving, then v2 squared minus v river squared is going to be a negative number. We can't take the square root. But physically, we know if we can't keep up with the river, there's no way we can even just go straight back upstream and remain at the same location relative to the ground. So we have to be able to travel at least as fast as the river in the water in order to be able to travel across the river in the shortest possible distance.